Hello, Weld Central High School students. My name is Larry Newcomer. Before I became a substitute teacher, I spent time in the mining industry, and I'd like to tell you about my career. Now, I know a lot of you are here for Career Day because you're kind of stuck and you don't know where to turn concerning a career. Have you considered metallurgy? Most of you don't even know what that is. Now, what is metallurgy? Well, metallurgy is basically the science of separating metals from their ores. And an ore is a material that can be economically processed. You can make money processing it. It's the science of making and compounding alloys. It is also the science of making, shaping, heating, and treating materials for desired shapes and properties. Normally, metallurgy is divided into three specialties, or other compounds from the gangue material or the waste. So you're separating ore from waste, and you're using physical properties in order to do so. Is one material denser than the other? Is it a different color? Is it magnetic? Does it conduct electricity? Physical properties. Another area is extractive metallurgy. That's once you get the concentrated ore that you actually separate it chemically. And you have to use either chemical means, thermal means, or use of electricity. Third is physical metallurgy, where you have the selection and development of materials for manufacturing and construction through either alloy composition, where you add additional materials to the metal, or you actually modify the crystal structure. You can also get in with physical metallurgy, you can get into failure analysis, or you can get into welding technology. Now, if you're going to get into metallurgy, obviously you have to be interested in the hard sciences. In your first couple of years, you're going to be taking courses in math, chemistry, physics, material science, and basic engineering. Once you get through that, which is primarily your first 2 years, you will be taking courses, if you get into the metallurgical end, in comminution, which is basically crushing and grinding, in sizing, which you're separating by screening or other means of classification, concentration, again, where you're separating materials by physical or chemical properties. Is it denser? Is it a different color? Is it magnetic? Can you attach an air bubble to it by modifying the surface chemistry? You also get into dewatering, solid-liquid separation. You can get into hydrometallurgy, where you're actually using a solvent. You get into pyrometallurgy, where you're smelting and refining. You get into electrometallurgy, where you're utilizing electrolysis. You can get into welding metallurgy, corrosion engineering, failure analysis, why did something break? Or you can get into the physical metallurgy, again, the casting, shaping, alloys, heat treatment. One simple example we'll just call from pyrometallurgy, silicon metal production. Everyone knows what a piece of quartz looks like, okay? How many people have seen an actual piece of silicon metal? This is silicon dioxide. This is just the silicon. How do you get there? Well, you've got to study a little bit about thermodynamics. It gets kind of complicated here. We can blow it up, and what you can see is that if I add carbon, if I get out here about 1700 degrees centigrade, okay, I can actually take the oxygen away from the quartz. But I have to get it up around 1700. That's about 3000 degrees Fahrenheit. Well, okay, so we need to add carbon. In a silicon metal furnace, you will add wood chips. You will add bituminous coal. You will add coal that has been cooked and had the volatiles taken out of it, known as coke. You put that into an electric furnace, heat it up to around 3000 degrees, and you get silicon metal. Now, you get into the physical metallurgy, where you get into phase diagrams, time temperature transformation diagrams, microstructures. There's a difference between these two materials. Many of you have seen this material before. This is from a Chevy truck leaf spring. It's 5160 steel. If you watch Forged in Fire, they make a lot of knives out of this stuff. It's 0.6% carbon. So it would fit over on this part of the phase diagram, this has 1% carbon. It's a grinding ball. It is much harder. This bends. Obviously, you know a leaf spring bends and doesn't break. You put that much stress on this, it will break. But then this is much harder. It wears out much slower. So you take that, you start looking at these structures depending on how much is in it. But then if you take one particular area, you can have the same carbon content, and you can have different microstructures at different temperatures, even though the chemical composition doesn't vary. So you can get different microstructures. Now, if you take those microstructures and you move it over here and you start to cool it down, you can get different compositions of those microstructures. You can create things like austenite, pearlite, martensite, bayanite. It can get a little bit complicated. At this point, you're probably saying, my brain is full. Yes, I know. But once you get into it, you'll find out it's quite exciting. Where do you work? Well, you could be working in an office in an engineering company where you're doing design of a process and a plant, or project management. You could be working in a laboratory where you're doing research. You could be doing quality control. You could be working at a mine site, which is where I spent my career, in the technical supervision and management of a mine site. You could be working in a metal refinery where you're making the pure metal, the pure gold, the pure silver. You could be in a manufacturing facility where you're making something like roller bearings. It could be any of those places. So now you're saying, okay, I went to school for all those years, and I thought metallurgy was this big. But really, metallurgy is this big. And when you come out of college, you're going to know this much about it. So where are you going to get that additional information? You will get it because there will be someone there that will be mentoring you, that will be coaching you on the very specifics, where you can get the detail and start to get the depth in the specific field of metallurgy you want to get into. There are companies out there that still have co-op or intern programs even for people before they graduate. I looked up and found out United States Steel and Newmont still have those. You can get into an associate program where you may not get to your job for 12 to 24 months while you're learning the overall business. United States Steel still does that. If you end up working for a company like Rio Tinto, you could be at a very remote mine site. What they're doing is they're doing online sessions with peers so they can get a chance to talk to each other and learn. What do metallurgists make? Well, the websites say you're somewhere between $76,000 and $109,000 a year. What about when I first get out of college? The latest information says you're between $68,000 and $70,000 a year is what a beginning metallurgist makes. Where do you get metallurgical and materials engineering schooling? There's not many schools left in the United States. In fact, my alma mater, Penn State, does not offer it any longer. They do material science, they do not do metallurgy. Schools that still have metallurgy and materials engineering: Colorado School of Mines, Missouri University of Science and Technology, Montana Technological University, New Mexico Institute of Mining and Technology, South Dakota School of Mines and Technology, and the University of Utah. I just got a few slides to add here of places that I personally have worked at throughout the years. This was a iron ore plant in Minnesota where we ground up the material in 27-foot diameter mills, separated it magnetically, rolled it into little balls, and then fired it in a kiln and made taconite pellets. Again, this was another plant I worked at in Missouri. Again, you can see some of the magnetic separators. You can see some of the disc filters that separate solid-liquid separation. This was flotation, where we were actually floating the silica out of the iron ore to try and upgrade it. I worked at a nickel mine in Oregon where we actually used silicon metal to reduce the ore to make iron nickel. And again, that was a pyrometallurgical process. Again, I spent some time in Colombia, South America. That was a little different process. They actually used carbon reduction inside a large electric furnace. This is inside a furnace. That is a 6-foot diameter electrode. There were 3 electrodes in there. That furnace was pulling 50 megawatts of electrical power. Again, the silicon smelter we talked about, you put it in a furnace, that's what a silicon metal furnace looks like at the top. It just looks like a great big house fire with electrodes stuck down in. Again, you get into gold processing. This was a plant I visited in Brazil. Again, you got grinding where you have to grind it up fine, and then they were separating out the gold concentrate using flotation, attaching air bubbles to it. This is in Australia. A little project here called Tropicana, kind of out in the middle of nowhere. This happened to be a 24 foot by 43 foot diameter ball mill. 35% of the volume of that mill was full of these balls. It was being turned by two 9,400 horsepower motors. I got the opportunity to work on helping with the commissioning of it. Again, this was a plant I worked at, helped with the commissioning in the high plains of Bolivia. You can see the grinding circuit, you can see the classification for the cyclones. Interesting thing is, when the mine ran out of ore, where did all this equipment go? Well, I found out later talking to another metallurgist. I was here helping to commission this. He was helping to commission the same mills, only this got sold and reinstalled in Egypt. Now, where are we having the conversation? We're having this conversation about these mills that ended up two different continents. We're in Australia, in the outback. Small world. This was a processing plant I worked at in Nevada, where instead of doing wet grinding, we did dry grinding, and we were trying to get the carbon and the sulfur out of the ore. We were using a whole oxygen fluidized bed roaster to do so. This is Cripple Creek, Colorado, gold mine, where they actually take the rock and you put a dilute cyanide solution on it, and you dissolve the gold out, then you absorb it onto activated charcoal, then you strip the activated charcoal off, then you run it through an electrowinning cell, you produce a sludge, and you make gold buttons. And you end up with little gold pieces. You end up with silver. Those are actually from that mine. And to finish up, yeah, some people may feel this way about metallurgy. I blame society for putting me here, but mostly I blame metallurgy for keeping me here. Thank you. Have a good day.